Okay. Please, Kalyan, put a WhatsApp message to all the students in your
Okay.
WhatsApp group.
Yes, sir.
Less number of students are there. Okay. Yeah, just a minute. Just give me a minute, 1 minute. I close some files, then I come to you. Are you able to see my slide?
Yes, sir.
No.
Okay, okay. So yesterday we discussed knuckle joint. Today we are going for a couple of problems. Then we move to the next topic, threads. Now, just to recap what we discussed yesterday, we discussed up to this, no, yesterday. We completed, no, all shear force, tensile force, crushing force acting in the knuckle pin, iron, fork, and we completed, right, yesterday? Someone reflect, boss. Hello?
Yes, sir.
We completed or not this portion?
Yes, sir.
Okay, but thank you. Okay. Now, just to recap, then we go for the problem. Now, in the knuckle joint, we are using three components. Main components, knuckle pin, iron, fork end. Fork end, the other name is called two iron. Two iron. And also this joint is also called forked pin joint. Forked pin joint. In this, I mean, we could discuss yesterday based on, I mean, the dimensions of the joint, dimensions of the component can be defined based on the failure condition. I mean, we considered first the rod, two side the rod we considered, and I mean, due to tensile behavior, we found that, I mean, due to tensile behavior, sigma t is equal to p by 5 by 4 d square, capital D square. We able to find out the rod diameter capital D here. But just to recap, okay? And tensile behavior, and I mean, pin is subjected to shear, two shears. Here one shear, this region. I come to take measure. This region here, this region here, right? Then pin is going to have two shears in this. Then P by 5 by 4 d squared. Pin, I mean, due to shear, double shear in the pin. Okay, that's also we discussed. The second thing, shear failure of the pin, P by 2 into pi by 4 d squared. This two region. Hence 2 into pi by 4 d squared. And later we discussed about that crushing failure of pin with respect to I. Crushing failure. In the crushing failure with respect to the compressive load, hence here that we discussed already, that is the in the force equilibrium condition, I mean mechanical equilibrium condition of each component. While discussed that time, we discussed this also. I show you that. Okay, here I think so. Yeah, here. See here. Due to compressive stress, there is a crushing shear. Crushing failure. Sorry. Okay. I mean crushing failure. Of the pin. This is the pin with respect to I. This I end is connected here. Okay. Now that's what we are saying here. Yeah. Now that is nothing but P by 2 into pi by 4 d square. That is shear failure of the pin. Crushing failure of the pin, P by L into D. I mean, this is the length L we are considering in the pin length L. Here D. This diameter is D, then P by LD. But you may say that here crushing failure based on the I end, based on the I also you can say that this is already we know the diameter, the width is, thickness of the I here is B. Then P by BD, P by force divided by BD, but we are considering both because it may be a different material. Then we need both in both. Based on this both component, we have to analyze the crushing failure. That's what we are considering. P by BD in the IN crushing, and the crushing failure with respect to fork. The pin is with respect to fork crushing. How many here? Crushing failure. Here also compressive load is acting, hence crushing failure due to fork. See here, sigma C equal to crushing failure with respect to fork. From the fork, the pin. See here, how many? This is a two crushing failure in the two places. Hence, this is a thickness is A into D, diameter of the pin, A into D, then two surfaces, then P by 2 into D, crushing failure of the pin with respect to fork. Now, then after that we discussed about this, and we discussed that tensile failure of the I. Tensile failure of the bending failure of the pin. Bending failure is nothing but 32 by d cube into P by 2 into A by 3 plus B by 4. Here the bending failure with respect to bending failure with respect to shear stress of the shearing failure of the pin, we are going to find out the B. We are going to find out the B value. I think B value or D value, whatever. Which one is maximum? A D value. The D diameter of the pin we are going to find out from this here only. I mean, which one is more diameter, that only consider with respect to bending stress, with respect to shearing stress, permissible shearing stress. We are going to find out the diameter. Which one is maximum value, that will be considered for the design purpose. That's what. And later we discussed about the tensile failure of the eye. Tensile failure of the eye. Where is the tensile stress is acting the eye end? See here, tensile. Yesterday I didn't show you that figure. Yeah, I already shown here. This is a tensile failure. Come to equilibrium diagram, then you can easily understand. See here, this is a tensile load acting in the eye end. Hence, this only we are considering now. This is the projection area. See here, I mean, this region going to be subjected to tensile. Hence, D minus D naught. This is the outer diameter of the fork. Both fork diameter, outer diameter of the fork. This is eye, outer diameter of the eye. Both are same. Then this is the capital D naught. Sorry, D naught minus T D. I mean, this is the pin dia into B, not T, into B. That is going to be a tensile failure of the eye end. See here, tensile failure of the eye is given here. Okay. Now, tensile failure of the fork. I mean, only this thing only changing. The earlier case here we considered, I mean, width of the, thickness of the fork. Sorry, eye end. Thickness of the eye end. B is nothing but thickness of the eye. Now, here also going to have a tensile failure of the fork, right? Hence, these two thickness going to be involved with, instead of B, the two thickness going to be involved. Hence, remove this B here and put it 2A here. Then going to come, sorry, 1 minute. I take another color. Now, if you put 2A here instead of B, if you put 2A, you are going to get, that is a tensile failure of the fork end. Two ends are there, not two eye ends are there in fork. Then we are multiplying 2. That's all component we discussed. Now we move to the one problem. And this is also I showed or not. Yeah. Yeah, do you have any doubt in this up to this? I mean, this is the, what is this here? This is the thickness of the fork. Thickness of the fork 0.75 D from the design data book. This is B is the thickness of the eye end. Thickness of the eye. I mean, this is the 1.25 D. This is the diameter of the rod. Okay, this is the diameter of the pin head, 1.5 D. Okay, these are the things standard we have to use. Here, this is a D naught. What is a D naught? D naught is the outer diameter of the fork or eye end. Fork or eye. Here, this is outer dia. This is, if we consider, this is outer dia. Okay. Now these are the things we discussed actually now also. Okay. Now we move to this is a step to be followed with the problem. Now this is the things I forgot to say yesterday. I mean, this is a general procedure to design the knuckle joint. I mean, let P be the axial force transmitted. We should know how much force going to be transmitted. I mean, step 1, determine the diameter of the rod. Step 2, draw the neat sketch and fix the various dimensions using in the proportions. Very important. I mean, if you go any books, this is a standard calculation for knuckle joint and quarter joint. You may expect this kind of question in the end sum. You have to be clearly drawn the figure. I mean, once you find out the dimensions of the component, you have to draw the figure and identify the components dimensions in the figure. Okay, very important. So please practice. These only three problems. We can't go beyond that. Because we discussed all failure analysis. that can be considered for this, defining the dimensions of the each component. Okay. Then final step is check the shear strength, check the strength of the joint for various failures. Now I come to the problem. Yeah, it is required to design a knuckle joint to connect two circular rods subjected to an axial tensile force 50 kilonewton. Okay, the P value is given 50 kilonewton. The rods are coaxial and a small amount of angular movement between their axes is permissible. Okay, now design the joint and specify the dimensions of the components. Select the suitable material for the parts. Anyway, material. How we are choosing the material? But anyway, this should be a given data. Okay, this is it should be given data, or you can take it from the design data book. Okay, now it's how to select the material. We have to understand now. The two rods are subjected to tensile force. Hence, yield strength criteria is very important parameter for selecting the rods. And the pin is subjected to shear and bending. The shearing strength and bending strength is important parameter for selecting the pin. Okay. Now, these are the things we have to consider. On the strength basis, the material for two rods and pin should be selected plain carbon steel. 30C8. Here 30C8. Yes, the yield strength is going to be 400 Newton per mm squared, corresponding this. Corresponding the designation of the steel grade, yield strength is 400 Newton per mm squared. Okay. Now, the yield strength is always yield strength. Yield strength in compression is at least equal to yield strength. Suppose yield strength is compressive strength is not given, you may consider at least equal to the yield strength. But always, in practical condition, compressive strength always greater than the yield strength. Even we discussed two problems. In those problems, compressive strength we consider twice the yield strength. Okay. Now I come to this. This is a selection of material with respect to components. What are the stress component is involving, like that. Now I come to the selection of factor of safety. What are the factor? How to choose the factor of safety? In stress analysis knuckle joint, the effect of stress concentration is neglected. We already, whatever formula we derived, we discussed the design of the component, the dimension of the component. During that time, we assumed that is stress concentration factor neglected. Because why we are neglected? Even those holes are there, but we didn't consider stress concentration factor. Okay. Now here the higher factor of safety is 5 is assumed to be the this design. Suppose factor of safety where I can use more, where I can use less. Please, someone tell me that. Again I ask you clearly. Factor of safety, higher factor of safety, which component I can give, and low factor of safety, at which component we can give. Please. Yeah, someone tell me that, please. I come to this also.
For pin lower, for forks higher.
Yeah. Any reason, please? Thank you for reflection. Any reason?
Sir, we have keyways and eyes on the in the components. So we should take higher factor of safety for that.
Okay, valid points. I'm getting some reflection. Yeah, okay, valid points. Okay, anyway, in the quarter joint also we discussed because see here the components fork end, eye end are complicated design, complicated structure, complicated design, and the complicated design and also it take more cost. It is a more cost as compared to pin. Okay, complicated design, more cost, and manufacturing time also will be more required as compared to pin. Pin is simple design, simple design, and it can be easily manufactured. The cost of pin also less as compared to your fork and eye-end. Okay. Now, if I give fork and eye-end, I mean factor of safety, for example, 6, then I have to give factor of safety for, I mean, pin, maybe we can give for 4 or 5. Because once the failure happens, only this component, the fin component, going to be broken. Okay. Then these components, the fork or eye end, not damaged. Hence, we can prevent the damage from, we can prevent the failure or damage from the component while functioning the component, while subjected or while transmitting the power. Hence we can provide less factor of safety for the pin. Then even though failure, we can easily replace the component and less cost and less, I mean, as well as less cost, and I mean the design also not complicated one. We can easily make them, and you can easily dismantle and assemble it. Okay. But unfortunately, if broken fork is going to be broken, then it will be a problem. Okay. Hence we have to give more factor of safety for fork and eye end instead of pin. Okay. Pin is, we always try to give less factor of safety. Even if failure occurs, the other components going to be saved. Now, this is the problem. Now we have discussed about this factor of safety. Now I come to this. This is we consider here factor of safety 5 for this problem. Okay. Now, I mean, crushes yield strength is 400 Newton per mm square. Factor of safety given. This is a permissible stress. Now, crushing stress is given. Crushing stress, we assumed that equal to yield strength. Hence here 400 divided by 5, 80 Newton per mm square. But shearing strength here given, I mean, this is a standard 0.5 times of SYT, yield strength divided by FOS, factor of safety is 40 Newton per mm square. Okay. Now calculation of the dimension, one by one we do now. First we define the material. Second we define the factor of safety. Third, we calculated the permissible stress limit for the components. Then fourth step is going to, I mean, in the fourth step we are going to have calculation of the dimensions, whatever we discussed early. Based on that formula, we are going to calculate the dimension of the each component. Now I consider diameter of the rod, while the rod is subjected into tensile force, right? Then tensile force is the permissible tensile stress is 80 Newton per mm square. Now this is the sigma T. Sigma T is equal to P by A. Sigma T is equal to P by A. From this formula, we are able to find out diameter of the rod is 30 mm. Okay. Now, once we find out the diameter of the rod, the enlarged diameter, this rod, the enlarged diameter here in this figure not shown, but yeah, this one in this figure shown here, the enlarged diameter is now D naught. I think D naught or D1. Okay, I think D naught. D1 per D1. This is D1. Now D1 is from the standard calculation from the design data book 1.1 times of D, then 35 mm D, the enlarged diameter of the rod. Now I come to the dimension of A and B. This A is nothing but our thickness of the fork. B is nothing but thickness of the eye end. Okay. Now A is a 0.75 D, and A is 0.75 D, and B is equal to 1.5 D. Then from this we can find out 25 mm, 40 mm. This is a design data book. Okay. Now the diameter of the pin. This is the diameter of the pin based on the shear stress acting in the pin. The pin is a 2 places shearing stress. Then tau is equal to P by, right, and P by pi by 4 D square. This D square is the diameter of the pin. Okay, P we know, tau is the permissible stress we know. Only D square we want to find out. This is a 30 mm. Now, but as I told you that early, we have to follow this here two formula or two steps. One is the diameter of the pin going to be considered based on the shearing stress. The diameter of the pin is going to be considered based on the bending stress of the pin. Then this is the bending stress of the pin. I mean the diameter is evaluating based on the bending stress of the pin. Then the diameter here we have found that 40 mm. Now which one is higher diameter that can be considered? This is our designed diameter. This is the consider for the design. Now dimension of D0 and D1. What is D0? This is outer diameter of the fork or eye. D1 is nothing but our, pin head diameter. Pin head diameter. Okay. Now D0 is equal to 2D, 80 mm. Here, 80 mm. This one. Okay. Now this is our pin head is 60 mm. Pin head is 60 mm. Now all the dimensions we have found it, and you have to draw clearly each component dimension you have to point out in your figure. Okay. Now come to the last step. Come to the next step for checking the stress types. Whatever we define the dimensions are, we are going to check within the safe limit or not. That is the final step now. Now this is the what is this? This is the tensile failure. Tensile failure in the I end. P by the tensile failure in the I end P by B into D0 minus D. We know already B. We know D0. We know D. We know P. Then this is our tensile failure is 31.25 Newton per mm square. Sorry. This is less than the permissible limit, sigma t less than 80 Newton per mm square. Then this is the suitable dimensions. Now we are coming to the crushing failure. Crushing failure, I told you that this is the I end. Crushing failure P by BD. Then we know B value and D value. This also 31.25. Finally, this also less than 80 Newton per mm square. Hence, this we are in safe limit only. Our design in safe limit. Now shearing failure. Shearing failure of the pin. Shearing failure of the fork. Oh, sorry. This is I because B is presented I only. Shearing failure of the I end. Then this is a P by B into D0 minus D. From this, we are able to find out our shearing stress of the permissible shearing stress of the practical shearing failure of this shear stress. This is less than 40 Newton per mm square permissible limit. Now this is with respect to I end. Now this is with respect to fork. Now this is a tensile failure 2A into D0 minus D. This is the tensile failure. Tensile is going to be 25 Newton per mm square. This is the less than the permissible value. Now this is going to be crushing failure in the fork. Here, crushing failure in the fork. Then this is a 25 Newton per mm square. Finally, the shearing failure of the fork. Here, this is a 2 shear. No, this is 2 shearing failure in this region. This region. Okay, then P by 2A into D0 minus D, then 25 Newton per mm square. All are in less than our permissible limit. So whatever we defined the dimensions of the component is suitable for making the joint, and we are within the safe limit. Okay, that's all. So now, if you have any doubt, please ask me that. I'm ready to clarify your doubts. Then we go for the next topic, threads. Yeah, this evening I will share you these slides. I come to home screen. Yeah, guys, if you have any doubt, please go ahead. Okay, shall we start threaded joints? Hello?
Yes, sir.
Okay. I think threaded joints, we are using lot of bolt and nuts in our mechanical applications. It's not only limited to mechanical application. This is even if you consider civil engineering, mechanical engineering, I mean electronics industries, electronics and electrical and electronics, everyone, then everyone is using threaded type of, I mean everyone is using nut and bolt, right? But the thing is, we are using big nut and bolt for mechanical application and civil engineer application. We are using very big size of nut and bolts. But I mean electronics and electronics industry people, they may be using very small size of nut and bolts, right? That's the size only matter, but not, I mean whatever the size is matter and the applied force is matter. But mechanical applications, we would like to transmit large amount of force, hence we are using bigger size of nuts and bolts. But electronics industries, they are using for just holding the components and sometimes they are using for the application, right? Holding the components and tightly fixing the boards in the mounting the boards. They are using nuts and screws, bolt, nuts, screws. They are using, right? But the size is different, and apply the force on the nut is different. That's all. But the size and force are different. I mean, mechanical engineering, but the civil industries, civil engineering, they are using very big size of nuts and bolts. You might have been seen in the construction building. They are using bada size nuts and bolts, right? There are a lot of number of nuts they are using. But before and now we are going to deal in this topic types of nut, okay, and types of nuts and bolts, and what are the forces are acting in the nuts and bolts. We are going to discuss in that. Okay, first, nut is a temporary joint, right? Bolt and thread, thread and bolt, nut and bolt, using for connecting or joining the two components, that is nothing but temporary joints, right? The threaded joint is defined as the temporary joint of 2 or 3 machine components which can hold securely as a temporary joint, right? That's all. See, clearly you can understand. It's very simple only, but everyone, very simple in that sense. As a mechanical students or even mechanical, civil, electrical, everyone must have been used this bolt and nut sometimes, right? That's what you can easily understand this topic, no doubt at all. Okay, the threaded fastening means that bolt and nut items are used to join the mechanical component, to join the two components. The threaded fastening means that bolt and nut components are used to join two mechanical components, right? Mechanical components are used to join the mechanical components. There is a temporary joints, and it can be easily dismantled and assembled without damage the components. What is the nut? What is the bolt? Bolt means, what is a bolt? You might have been studying the first year. The helical groove, continuous helical groove is formed on the thin, plain cylindrical rod. Continuous helical grooves is formed on the plain cylindrical rod that will be acting as a threads. See here in this figure. This is the thread angle. Okay, first we see from here. This is a pitch. Okay, first we start from, what is a crest? This is a crest. This is a top portion. This point is a crest on the. Okay, this is a crest. Okay, this is a root. the below the part, in this part, this position, this is the root. This is the root. Okay. Now the flank, this is the flank region. Okay, here to here not clear. I will show you later figures. Just to keep in mind. Anyway, we are going to discuss the thread. Terminology, threads terminology during the time you can understand. Okay. Now this is the minimum diameter. This is the minimum diameter. This one. Without a threaded portion, minimum diameter. And this is the maximum diameter from top, this crest to this crest, bottom crest to top, crest, maximum diameter. Okay, I mean in between, this is pitch diameter. This is a pitch diameter in between. This is a pitch diameter of the nut. Okay, now the nut is encaged inside the bore. The nut is encaged inside the internal hole. The internal hole is nothing but a tapped thread. There is internal thread. Tapped thread, nothing but here internal thread. The bolt is inserted inside the internal thread. Hence, this is internal thread. This is external thread. Sorry, this is external thread. Now the angle, this is the angle, thread angle. Thread angle is nothing but, the angle between two crests. The angle between two crests, the inclined surface, that is theta, thread angle. Now this is the depth of the thread. This is the depth of the thread. Depth of the thread. Then now, can you tell, how can I find out the depth of the thread? I already have given you mean diameter. It's from the plane portion. Mean diameter, minor diameter, and major diameter on the top crest to bottom crest. Major diameter. In between middle is pitch diameter. Now, can you tell me the depth of the thread or thickness of the thread? What is the thickness of the thread?
Major diameter minus
Yes.
Minor diameter.
Yes. Major diameter minus minor diameter. It should be divided by 2 or not?
Yes, sir.
Missed out. No? Okay. So thickness of the thank you, Pa. Thank you. This is the thickness or depth of the thread is nothing but major diameter minus mean diameter, minor diameter divided by 2. Now, you should know this is the component. What it is, you should know how to locate. This is the crest, this is the root, this is the flank, this is the major diameter, this is the minimum diameter, minor diameter, this is the pitch diameter, this is internal thread, this is external thread, this is the thread angle, this is a pitch. The distance between one crest to another crest, distance between two crests. The distance between this crest, one crest to another crest, is called pitch. Okay, pitch. Now this is the depth of the thread. Also, you know very well. Now I come to the how to measure the size of the bolt and nut. Okay. Now see here. This is the body length. This is the body length where we are going to join two components. For example, two plain plates going to be held or tightly gripped in this region only. This is the plate 1. This is the plate 2. Then here only going to be tightly gripped, right? Then this is the region of body. This is the region we are saying that body length. This the region is body length. Now, this is a transition zone. Transition zone means that you can see here, you take any nut or any bolt, you can see that there should be some tapered kind of dimension should be there, because when you are using nut here, the nut you can't use up to entirely, you can't use the threaded portion. We have to use slowly we have to reduce to avoid the sharp corners here at the end of the this side of the bolt. Okay, that is called a transition length. This may be 1 mm or 2 mm, depends on size of the nut they will provide it. Okay, this is the total length of the bolt. Total length of the bolt. This is a flange height. I mean, even you might have been seen nowadays the nut is a flange. I mean, you may avoid using external washer, such a kind of bolt. I mean, if it is not there, the flange is not there, then we have to use the washer, thin washers. Now, this is the flange height. This is a head height. Head height is nothing but, I mean, where we are accessing the bolt using spanner. So this is the head height. This should be standard for accessing the bolt. Because standard in that sense, I mean, as we studied already, the components, whatever we are preparing, we have to follow the standards. I mean, BI standard or international standard, right? Because we cannot manufacture 1,000 varieties of nut, 1,000 varieties of head height like that. Then we cannot. Then we have to search appropriate spanner for tightening the bolt, and we have to follow the standard dimension. Okay, this is the head height. This is a body length. This is a threaded length. This is the threaded length. Threaded length. This is the minimum diameter. I mean, this is the mean diameter, minor diameter. This is the major diameter. This is the in between. This is the pitch diameter. Pitch diameter. This is the hexagon bolt and nut. This one. Hexagon headed. This is hexagon headed nut. Hexagon headed nut. Sorry, bolt. Hexagon headed bolt. Sorry. Okay, now see here also clearly given, this is a thread nut, this is a run out, this is shrunk. The plain area you also said that is shrunk. Plain area you can say that is shrunk. Now this is the bolt head. Okay, this is a grip length, what I told you earlier. I mean, you can say, I mean technical term here, this should be a nominal length. It should be used nominal, but here they use length. Now, most of the book they are following nominal length is a correct one. Please consider that. This is the one. Now, this is this. I mean, square-headed bolt. Square-headed bolt. This one. Okay, square-headed bolt. I mean, based on application, we have to choose our bolt design. For example, I mean, civil people they are using this type of bolts mostly. Okay. Now, what is the advantages and disadvantages? We see some few points we discussed, because I mean there are a lot of advantages and I mean few disadvantages also should be there, but we see some few points. Okay, here the parts are held together by means of the clamping force using nut and bolt assembly, right? I mean assembly, then there is no loosening the parts. I mean, because this is no loosening the parts means that we are tightening the bolt and nut. It's not less possible for the loosening the parts. It may take time. I mean, how much your load or force acting in the components depends on load and load, depends on I mean condition, static condition, dynamic condition. Okay, the possibilities of loosening the nut and bolt. But even loosening, then it can be easily tightened. Then we can maintain the appropriate gripness between the components. Okay, that is an advantages. The parts are assembled means of the spanner. Okay, the length of the spanner, whatever we are going to use the spanner, the length of the spanner is large compared to the radius of the thread. I mean, you might have been seen large compared with the radius of the thread, because the mechanical advantages is more for the mechanical advantage is more, and the force required to tighten the joint is small. I mean, the spanner length will be always more than our radius of the thread. Then only we are able to access the nut easily. Then only able to apply more force. to the bolt or else nut for tightening the component. Hence, the mechanical advantages is more in this while using mechanical advantages more while using more length of the spanner. Okay. Now, some of the this is the suppose as a mechanical engineer we should know why we are using more length of the spanner, right? And more length of the spanner, the mechanical advantages will be more, and the less amount of force it will be applied to grip the component. Creating more torque between the components and bolt and nut. Okay. For tightly holding the components. Okay. Now the threads are self-locking, therefore threaded. Anyway, we are not discuss as of now self-locking. We will discuss in the later. But a few advantages I am telling here. The threads are self-locking, therefore the threaded joints can be placed. In any position. This bolt and nut we can use at any angle of orientation in the components. Okay. And the threaded fasteners are economical to manufacture. Their manufacturing is simple. High accuracy can be maintained in this, because high accuracy in that sense, you might have been seen. Coarse thread, fine thread nuts. Coarse thread nuts. The pitch diameter, whatever this is a pitch, right? The distance between two crusts is called a pitch. The pitch diameter, pitch is even you can see 1 mm, 0.5 mm. I already have seen 0.5 mm, 0.25 mm pitch thread. When you are going for 0.5 mm, 0.25 mm pitch thread, it's smooth action can be done, and it will be smooth action and high accuracy. High accuracy while gripping the component, we can apply high accuracy of torque also. Through bolt head or nut. Okay, that's what. Many manufacturing is simple, right? As compared to welded joint, especially I'm saying that. Okay, this is cost of the joint is less as compared to welded joint. But welded joint we cannot compare here because that is permanent joint. Okay, okay. Now the parts joined to the threaded joint can be detached and easily detached, and it can be easily attached. Okay, whenever required we can easily replace it. For whenever required it can be easily dismantled, and it can be repaired, and it can be assembled easily. What are the disadvantages? Few advantages I told you that we would like to talk about the disadvantages. What are the disadvantages? Because advantages, everyone knows that. Please, can you tell me anyone about the disadvantages of the bolt and nut joints? Any disadvantages? Anyone? Please.
Sir, due to age, due to rusting, the bolt and nut may get locked, so it can't be opened.
Exactly. This is because here the threaded portion. The threaded portion may be the foreign particles going to be sedimented or dust going to be sedimented, and it may be a possible of corrosion, right? Then it will be jammed. Then when we are going to use long duration, that is one disadvantages. I agree. The another disadvantages, when we are using a threaded bolt, bolt and nut component for joining the two components, we have to prepare the holes in the component. Hence, while preparing the holes in the component, we are losing the strength in the components. Means that whenever we are preparing the holes, the stress concentration is more in the holes, right? Then when two components are joined with the help of the bolt and nut, then after that, the near the holes always stress concentration is more. Okay, that is the one disadvantages. But it depends on nut, depends on material. People try to avoid that. Stress concentration effect also. That's what we are using washers, and we are using flange headed bolt, like that bolts we are using to avoid that kind of issues. But still we cannot avoid zero. We cannot avoid 100%. Okay, this is one disadvantages. The other disadvantages, threaded joints loosen, then it will be the component is going to be subjected into vibration. So we have to be verified oftenly. The maintenance will be required. I mean, welded joint, there is not possible. The components, loosening the components is not possible while using welded joint. But in threaded joints, the threads are getting loosened. Then it will be difficult. Then it will be the component going to be subjected into vibration. Then that unnecessary vibrations may be a problem for the component, especially in electronics industries. They are very, very important, because when they are dealing with the nano size, micro size chips, and micro size components, and very, very small circuit boards, they have to securely fixed with the board. Okay, otherwise small vibrations going to happen, it will be a problem. So unnecessary short circuits may happen. So this is the another disadvantages. Okay, now we move to this some basic types of screws, nuts and screws. Okay, I mean, see here the basic types of screw fastening. Now one by one, see here. I mean, three parts of threaded fastening, right? Three parts of threaded fastening. One is bolt, screw, and nut. Bolt. This is the bolt, right? Bolt, nut. This is nut, right? And washer. Bolt, washer, and nut. This is the main components for creating the fastening or joining the two components. This is a component 1. This is a component 2. Okay. Now, a bolt is a fastener with the head and a straight threaded shank, and intended to be used with the nut to clamp 2 or more parts. That's what I told you here. This is a region what we discussed earlier. This is the body length. This is the region body length. This is the region body length, or thickness of the component, total thickness of the component. Now this is called a shank. SHANK. It's a plain cylindrical region is going to be called a shank. Okay, and this is, it should be a cylindrical rod. In the geometry is going to be a cylindrical rod. This should be a cylindrical rod. In this type of the types of screw fastening, we are considering through bolt, tap bolt, stud type. Now we are discussing about through bolt type. In this through bolt type, this is the plain rod, plain shape. The shank is nothing but plain shape. But this is the threaded portion. This is the threaded portion. This is nut. Okay, this is a nut, hexagon nut. This is hexagon bolt, hexagon headed bolt. Hexagon headed bolt. Okay, hexagon headed bolt. Now the threads, we already discussed the threads. What is the pitch? What is the thread angle? Okay, what is the mean pitch diameter? What is the pitch diameter? What is the minor diameter? What is the major diameter? Oh, those things we discuss later. Now just discuss about the types of screw fastening. Screw fastening. In the type of screw fastening, this is a through bolt screw fastening. Next one is tap bolt. In the tap bolt, now no need nut here, because the tap bolt, this is a component 1, this is a component 2. Then the component itself, the internal thread will be created, tapped thread. This is nothing but the internal thread created on the component, that is nothing but a tapped thread. Tapped thread. Now when we are joining these two components, then we are straight away inserting the bolt to tighten the component, to join the two components 1 and 2 with the help of the tapped threaded portion inside the component. Okay, here no need nut. We are not using any nut here. Okay, this is the tapped bolt. Now I come to the stud. Stud is nothing but here. Here also, this is the region. it won't be any thread. This is it's like, looks like a sunk region. The threaded portion going to be here. I mean, at least any one of the component must be in threaded portion. I mean, this at least any one of the component must be threaded portion. Then only we can access tap bolt for joining the two components securely. Okay. Now I come to this stud. I mean, through bolts. Some more points I note down that I tell you that. Okay. Now through bolt, okay, that's all. This is enough. But please go through your book. You can get into more information, so you can easily understand. No need to go for in depth. Okay, please you go through that, because this is the things you can easily understand. Okay. Now I come to this stud. Stud here. See the stud. A stud is a cylindrical rod, threaded both ends. I mean, here stud is cylindrical, threaded both ends. I mean, here also thread. I mean, this is a small region, maybe sunk. This is a small region. This is small region. This is a sunk. Okay. Now, I mean, that threaded this bolt here with the bolt, it won't have any head. See, the first one is through bolt. It should be head. It should be nut. But when you are going for tap bolt, it's not necessary. No need a bolt nut here. No need. Yeah.
Sir, it's 4:15. You told to remind.
Okay, ma. Now I stop it in this slide. Okay. Thank you for your reminder. I stop it in this slide. Okay. I stop it now. First, I complete this stud, then I stop it. Okay. The stud is the cylindrical rod. Both sides to be threaded portion. This also threaded portion. This also threaded portion. This also threaded portion. Okay. See here. I mean, here also the component should be tapped region. Tapped region means that internal threads. Then the stud can be easily accessed through the internal thread. Then another component going to be keep on this first component. Then I mean again the nut going to be used on the top of the stud. Top of the stud. I mean, stud is main difference. Both sides threaded, and here the nut is used on nut is used on the top of the one side of the stud. One side of the stud. Okay. So here one of the parts of the thick enough to accommodate the threaded hole. This is one of the parts should be enough to accommodate the threaded hole. Okay. The material of the part which with the threaded hole has sufficient strength. I mean, here it has been sufficient strength. I mean, suppose if you are connecting low strength material to aluminum plate, then it will be acting more stress or more load. Then better to avoid this stud. Suppose if you are taking stainless steel or mild steel, then it will be a more strength. Then it can be easy. Then you can use this kind of stud, the stud type of joints, because this is the material is more strength. I mean, even if you are preparing the internal threads, then it will be better. Then better strength can be obtained while joining these two components. Okay. Okay. Now I stop it here. The next class we discuss remaining things. We increase our speed also. Okay. Now I stop it here. Yeah, please go through this video and your book. I mean, next time I'm not going to give more explanation about this basic. So once we are going to discuss about the terminology of the threads, nomenclature of threads, we discuss in the next class, and we move to some problem. Yeah. I take attendance. Please wait. Roll number 1.
7, sir.
Guys, any doubt? Yeah, please. I didn't ask that. Any doubt? Chat box.